In last lecture, we learned about the gradient of a scalar field. We studied the physical significance of gradient and also solved different problems, take many applications to understand what does the gradient mean and their properties. And now in this lecture, because I have already told that initially I made the lecture a combined lecture of gradient and divergence, but due to the long length I had to split that. So now initially I decided to introduce the lecture for divergence and totally based on applications, but after all, I have also introduced the physical significance of the divergence in the last of the lecture. So, through this lecture, you will understand the definition of divergence. You will take a lot of problem solving through which you will understand the meaning and clear applications of it. And in the last, you will you will learn the physical significance of divergence. And because of the split of lecture, I have introduced a 1 minute lecture in intermediate time. So let us start with the definition of gradient. Already we learned that this delta operator is vector differential operator given by I del by del x, d del by del y, k del by del z, and we also discussed that these can be multiplied with vectors in two ways, because vectors have not simple multiplication. So either this is a vector, so this can be multiplied with a vector either in cross product or dot product. So when we take dot product of this operator with some vector, we call it gradient of the vector. So let v x y z is equal to v1 I plus v2 j plus v3 k be some vector, and we write dot product of delta with this means del dot v. So this is called divergence, and with the dot product definition of the dot product, it will comes out to del v1 by del x, del v2 by del y plus del v3 by del z. Means simply saying, if you take divergence of a vector field, then first component x component is differentiated partially with respect to x, y component of the vector is partially differentiated with respect to y, and z component of the vector is partially differentiated with respect to z, and you take the sum of all of the three. This is called the divergence of the vector. And now we will consider the dot product of the vector differential operator with a vector function. So if v x y z is equal to vxi plus vyj plus vzk, this is a vector function we already discussed in the same starting of this lecture. So del dot v, and actually there is no need to write bar on del. It is considered as a vector operator. So del dot v, this is equal to del vx by del x plus del vy by del y plus del vz by del z. So this is called divergence. This is called divergence of this vector function v. This is called divergence of v. And note that there is a definition. If divergence of v is equal to 0, we say that v is a solenoidal vector. Solenoidal vector. This is the name. We will discuss in next lecture or some other lecture what is the physical importance of divergence and why we say it a solenoidal vector. But remember that when divergence is 0, the vector is solenoidal, and this grade del dot v is sometimes also referred to del dot v, that we are speaking it divergence V. So this is sometimes written in shorthand as div V or div V. This is shorthand notation for divergence V. So we will also use these notations. Let us take an example. Find divergence V at 1 1 1 if V is equal to x square I plus xyj plus xyz k. This is the vector V and we need to find the divergence. So divergence of V is equal to, you know, formula is before you. This is the formula. So differentiate first component with respect to x. So this is 2x plus differentiate second component with respect to y, so this is again x, and then differentiate this third component with respect to z, so this is xy, and now put 1 1 1, so divergence of v at 1 1 1, this will become 2 plus 1 plus 1 is equal to 3. So remember that dot product, because dot product is scalar quantity, so divergence of a vector will be scalar quantity, while gradient of a scalar is vector quantity. So this is a scalar quantity. And as a next example, find divergence of R and R, where R vector is given by xi plus yj plus zk, and also remember is that sometimes in examination R is not specified. So if R is specified, you have to take that prescribed in the question, and but if R is not specified or not prescribed, it is always taken as this xi plus yj plus zk, means position vector. So now let us find what is the divergence of this. So in previous question we saw that r square is equal to x square plus y square plus z square. So what is R and I? R and R. What is R and R? R is this. So this is R to the power n x I plus R to the power n y j plus R to the power n z k. This is R and R, and we need to find its divergence. So divergence of R and R, this is equal to partial derivative with respect to x of first component plus with respect to y of second component plus with respect to z of third component. So let us start finding one by one. So what is del y del x Rn x. So first you differentiate x, so you get Rn. Then if you keep x and differentiate Rn, so you get Rn minus 1 del R by del x. And again we have used this in previous lecture and in previous questions, two questions earlier. So this is x by R. So we get it as R to the power n plus nx r to the power n minus 1 into x by r. So what you get finally is r to the power n plus n x square r to the power n minus 2. And similarly we find other partial derivative. So I am writing all collectively here, and uh, del by del x component. So first del by del x component, del by del x r and x, this is equal to r to the power n plus nx square r to the power n minus 2, and you will get the del by del y component in a similar way. So it will be r to the power n plus n y square r to the power n minus 2. This is homework to you to calculate. And del by del z r to the power n z, you will get is r to the power n plus nz square r to the power n minus 2. This is again homework for you to calculate. Now this the this this we have to compute the divergence of R and R. So divergence of R and R is what? Sum of these three. So you will get 3r to the power n plus n r to the power n minus 2 x square plus y square plus z square, and x square plus y square plus z square is again r to r square. So just put these things, so you will get 3r to the power n plus n r to the power n, and that means 3 plus n r to the power n. So there is an interesting fact that if n is equal to minus 3, del r to the power n r is equal to 0, means r to the power minus 3 r is solenoidal. So this is solenoidal, means you can say r by r cube is solenoidal. So keep it remembered also, and keep remembered this formula. This is equal to n plus 3 r to the power n. We will use this in next question. So that divergence of grade Rn is equal to n plus 1 r to the power n minus 2, where r is the position vector xi plus yj plus zk of some point xyz. So we have done a lot of work for this one, so we will reuse that. We have calculated in some previous question that grade Rn is equal to n r n minus 2 r vector. We calculated in some previous question, so you can go back to the video and see this, otherwise you can calculate this. And just in the previous question we calculated divergence of r and r is equal to n plus 3 r to the power n minus 2, sorry, r to the power n. In just previous question we calculated it, and this means you can write divergence of r to the power n minus 2 r as, just replace here n by n minus 2, so this n minus 2, so this is n plus 1 r n minus 2 r r n minus 2. This is just r and r. This is what we have calculated. This divergence of r and r is equal to this, so replace n by n minus 2, so you will get divergence of r n minus 2 r. This is equal to n plus 1 r to the power n minus 2. Now combine these two to find the required result that we want. Now divergence of grade Rn. So first put the value of grade Rn. Value of grade Rn is n r n minus 2 r. Then take n outside. So we have n divergence of r n minus 2 r, and then put this divergence of Rn minus 2. So we have n plus 1 r to the power n minus 2. This is what we were required to prove this, and we proved it. So you have to put all the things, means calculation of this and calculation of this together. We have already calculated, therefore I have used. So you have to calculate all these two things to find the result. And finally we will take a last question. So if f is given by x, y, I, f is a vector, plus x, y square z plus z square k, find the component of directional derivative, find the component of directional derivative of divergence f in the direction of outward drawn normal to the surface of sphere x square plus y square plus z square is equal to 1 at 2 1 2. So first understand what question is saying. So question is saying this f is some vector function. So first you need to find out the divergence of f, this divergence of f, then directional derivative of divergence will become a scalar function, then directional derivative means gradient, so then gradient of divergence of f, again a vector function, and then the component of that final vector in the direction of normal to this sphere at this point. So normal to this sphere is again gradient. So let us find the things one by one. First, find the normal. Let phi is equal to x square plus y square plus z square is equal to 1, and n be the outward drawn normal, means a normal that is pointed from the center to the surface, out a radial vector, outward drawn normal to phi is equal to 1. Then n is calculated as del phi, and that is 2xi plus yj plus zk, and we need to find everything at 2 and 2. So n at 2 1 2, this is 2 2i plus j plus 2k. So before proceeding, also find the unit normal. So unit normal is what? Unit normal, this will become this, and that means 1 by 3 2i plus j plus 2k. This is our unit normal. So we have done one task. We have obtained unit normal, unit outward drawn normal to the sphere. Now we need to find the gradient of divergence of the given function. So f was given as xy I plus x y square j plus z square k. So first find divergence of f. Divergence of f will be partial derivative with respect to x for this first component. So this will be y plus partial derivative of this component with respect to y, so this will be 2xy plus partial derivative of third component with z, so this is 2z. Now this is divergence, and we have to find its directional derivative. Let it be psi. So dd of psi is equal to del psi, and divergence of phi is that we have written psi. So this means I del psi by del x plus, and you know the definition, so why should I repeat this again and again? So I then del psi by del x, and that means 2i plus j del psi by del y, so 1 plus 2x plus k del psi by del z, so it is 2. And now again we need to find the directional derivative at 2 1 2. So now del psi at 2 1 2, del psi at 2 1 2, so this 2 1 2, this will be 2i plus 5j plus 2k. Now at a final stage, you need to find this dd in the direction of this n cap. So dd means del psi at 2 1 2 in the in the in the direction of n cap is given by is del psi at 2 1 2 dot product with n cap, and just take the dot product, you will get it as 13 by 3. And now because we have split the lecture into two parts, one for gradient and one for divergence, so the time length of the lecture allows me to discuss the physical significance of divergence. So initially, let us take the uh, example of a fluid flow and understand the divergence in that sense. And then on the basis of the same, we will understand these things for the other fields like magnetic field, electric field, gravitational field, and so on. So first, I have drawn a structure here. X-axis is marked in green, Y in blue, and Z in red. And let us name the corners so that we can identify the faces. And later I will discuss why I have drawn this structure. So let us name these as A, A dash, B, B dash, C, C dash, and D, D dash. With the help of these letters, we will identify the phase. Now assume a fluid has a three-dimensional flow. So let us assume that the fluid enters this particle and exits this particle. So we will conclude what is the residue of a fluid in the particle. Means if fluid is entering at some rate and exiting at some other rate, then either two things are possible: either entry and exit rate is same, or entry and exit rate is different. If both rates are same, the fluid enters will totally exit the element. If there is a difference between the rates, means fluid enters at a higher rate and exits at a lower rate, then there must be some increase of a fluid in the particle. For an example, you take a solid pipe, and suppose the pipe does not exert any resistance to the flow of water, like a glass pipe, ideal glass pipe, and you fill the pipe and start filling. So the water you fill at the one end, and suppose the pipe is like this inclined pipe, so the water you fill from this end will totally exit from this end. And as another example, if you take example of gas, the gas you will fill from this end will not totally exit from this end. So entry volume will not be equal to the exit volume, and the difference volume will be where? The difference in the volume will be filled in this pipe. So the difference in the volume that we have discussed here creates the divergence, and we will throughout this discussion understand a more precise way. So initially we suppose fluid has a flow velocity v. Suppose fluid enters the phase a dash b dash b at a velocity v x y z and exits at phase c c dash d dash d at a velocity v x plus dx y z. You might be thinking why I have taken dx. So let me clear that the sides of the cuboid that I have taken this dx in x side, dy in y side, and dz in z side. So this is the total volume. You can also calculate the total volume of the element as dx dy into dz. This will clear you what is dx dy and dz. So because fluid entering at the a dash bb dash phase has a velocity v depending on xyz, and it has traveled a distance dx, so there must be a change in that particular distance. So now let us analyze this. So what is the volume entering in the fluid? So you know that volume means what is velocity? Velocity is distance traveled per unit time, and if we multiply this with the area of the face, what is the area of the face? A dash b b dash, this area is dy dz. So this area into distance travel, this is the volume passing per unit time. So we will consider this volume and name it at volumetric flow rate. Volumetric flow rate means volume passing from a phase per unit time. So now volumetric flow in from the face a dash. Again I am repeating that volumetric flow in means volume entering from this face per unit time. This is equal to v x y z into dy dz. Similarly, volume exiting from the face C C dash D dash T is equal to Vx plus dx y z dy dz. So these are the volumes entering and exiting in opposite phases. So if these are same, then okay, the volume entering is equal to the volume exiting. If these are not same, means entering at a higher rate and exiting at a lower rate, the fluid will increase inside this element. So let us consider the difference. And what is the difference? Fluid increasing inside the element is equal to Vx plus dx y z, and because dy dz are common, so we take it common, minus Vx y z and dy dz. Now we will expand this with help of Taylor series. up to first partial derivative. So what will this give? This will give bxyz plus del v by del x minus vxyz, and whole is multiplied with dy dz del v by del x. This is del v by del x dx, and then you can now see that it has become del v by del x dx dy dz. So this is the rate at which the fluid is increasing due to flow in one direction. Similar phenomena happens in all the directions. So similarly the increase of fluid inside the element due to flow component in y and z directions. Flow component means velocity component. So this will become del v by del y dx dy dz, and del v by del z dx dy dz. So we have seen that these are the components wise increase. So what is the total increase? So total increase of fluid inside the element, this is equal to del v by del x. We will sum all these three, 1 2 and 3, and dx dy dz all are all common in 3, so we can take it del v by del x plus del v by del y plus del v by del z, and this multiplied by the infinitesimal volume dx dy dz. So we can find the right it as this is equal to increase in volume. This is equal to del v by del x plus del v by del y plus del v by del z into dx dy dz, and you can see this is gradient of the velocity v. So we will write is at del v dx dy dz. Now this is the significance if flow in is equal to flow out. So condition 1, if flow in equal to flow out, then there will be no increase of the volume inside the element, and this means del v dx dy dz is equal to 0, and because dx dy dz is a finite volume, so this is volume is not 0, therefore del v is equal to 0. So this we say that, sorry, this is del dot v, because this is vector del dot v. So this implies that del dot v is 0, and this we say that divergence is 0. This implies divergence divergence is 0, means flow in is equal to flow out. In some sense we say flux in is equal to flux out in magnetic or electric fields, and in other fields, in gravitational field also we say flux in or flux out is 0 if the divergence is 0, and in velocity we say mass in is equal to mass out, or volume in is equal to volume out if density is constant. And the second case is if there is there is an increase of mass or volume or constant mass, we can call it volume, inside element, then, and increase of mass means flow in is not equal to flow out, then and that means flow in is greater than flow out, means entering more and exiting less, then there means this implies del dot v, this is not equal to 0, and this in this case we say that flow or velocity has the divergence. Divergence is not 0, and already through this lecture we learned that when divergence is 0, we say we have a special name for this. We say it solenoidal vector. So solenoidal is a special name for divergence is equal to 0. So when a vector is solenoidal, flux in or flux out is same, or mass in or mass out is same. So this is the physical significance of the divergence. Finally, as a summary of the lecture, we learned what is the divergence, means definition of divergence, what is the physical significance of divergence, and when a vector is solenoidal, we also learned through several applications, several problem solving, and now the next lecture will be devoted to the curl of a vector function. So stay connected and keep watching, keep waiting for the next lecture.